Hi, in this video, I introduced the Pearson skewness coefficient. A big thanks to my AP statistics friend, Erica Chauvet, for helping me with the math sources. Here's a formula for it. The Pearson skewness coefficient is equal to 3 times mean minus median, the whole thing divided by standard deviation. First, I'll explain the idea behind this formula. And then I'll explain where that factor of 3 came from. All right, what's skewness? Skewness describes how data are not symmetric. A distribution that's like this, kind of bell-shaped, where most of the data are average, and about an equal number are larger, and an equal number are smaller than that peak in between, then we consider it symmetric or approximately symmetric, and it has no skewness. Skewness equals 0. Now, a distribution that's like this, where most of data points are kind of on the low side, but there are some data points, some outliers that have really high values up here, then we call it skewed to the right or positively skewed. Personal income in a country, for example, tend to be skewed to the right. Most people have sort of middle-class income. Some people have poverty-level income. But in terms of income, practically nobody goes below 0. Whereas it's possible to have a few people with very, very high income, the multimillionaires, the billionaires. So income in a country, things having to do with money tend to be skewed to the right. The skewness would be positive. A distribution that's opposite of that, where most data points have larger values, but there are some data points, some outliers with much smaller values, is said to be skewed to the left or negatively skewed. The skewness is negative. An example would be something like model year of cars in the United States. We're now 2024, so most cars on the road will be from the 2020s or the 2010s or maybe the 2000s. There aren't a lot of really old cars, but sometimes you see them. Sometimes you see an old car from maybe the 1970s or the 1960s. They're out there, but there are not a lot of them. In that case, it is a left skew or skew to the left. The skewness would be negative. Note that the technical definition of skewed, the statistical use of the word skewed, is contrary to the way a lot of people use it in real life, in everyday life. I have a video about that linked above, so check it out. But in this video, I'll just stick to the technical statistical definition of skewness. Skewed right means the tail goes up to the right, positive skew. Skewed left means the tail goes off to the left, like in this picture, and the skewness is negative. Now, what happens when data are skewed? Let's take this example of something that's skewed to the right. That means you have some data points that are very large. Now imagine computing the mean of this. This is a Greek letter mu. It's the symbol for the mean of a population of data points. When you compute the mean of something, you take the different values of those data. So x1 plus x2 plus x3, etc. And then you divide by how many data points there are. So if there are 1,000 data points, you divide by 1,000. Well, because you have some of these data points that are very large, that means some of these x values will be very large. Well, when you put a few very large numbers into your addition, the whole addition will be large, and you divide by 1,000, it will be large. So that means your mean will be large. When you have data points that are far to the right, then your mean, wherever it used to be, it will start going to the right. The mean tends to follow where the extreme values are, where the outliers are. Well, that's the mean. Now, what about the median? The median is defined as this point right here, where about half of the data are below it and about half the data are above it. So 50% of the data are here and the other 50% are there. Well, watch what happens if I want to create more outliers. It depends on how I do it. If I take some of these data points and I change them into very large numbers. So for example, some of these people win the lottery and they become billionaires and millionaires. Then these data points move over here and they become 3 new data points over there. I got more big numbers. I plug them in the formulas for mu, for the mean, and the mean gets even larger. So the mean will follow these red points. But what about the median? Will the median follow? No, the median is just sitting there and looking to the left, and it sees that half of the data points are still to its left. It looks to the right and says, oh, half the data points are still to my right. They kind of moved, okay? 3 of them moved from over here to over there, but they're still to the right of me, of the median. So the median's not going anywhere. You get more outliers to the right, the mean will move to the right, but the median will be like, I'm not going anywhere. If I move some of these points to the right, to the far right, then yeah, the mean may move, but it just moves enough to make up for the fact that it loses 2 points here, so it may move over by like 2 dots. So it moves over by just a tiny little bit. So when you have something skewed to the right, the mean will move to the right, but the median may not move at all. And if it does, it may not move by a lot. The median is not as affected by the tail as the mean. The mean will follow the tail along, and the median will not. Here's a meme about this. A lot of statistics students and teachers have seen this one. It's pretty famous. An outlier comes along like a large value on the right tail, and the mean is like ready to just turn around and follow it. That's what the mean does when there's an outlier, where there's a long tail. Whereas the median is like, what are you doing? In statistics, we say that the mean is sensitive to outliers, and the median is not as sensitive to outliers. All right, so here are some data sets. They come with a couple of lines. The red line represents where the median of that data set is, and the green line represents where the mean of that data set is. For the distribution number 1, most of data are in the middle, and there's an equal number on the right as there are on the left. So the whole thing is symmetric, and there's no skewness. Skewness is 0, and the mode is in the middle, the mean is in the middle, and the median is in the middle. So for a bell-shaped curve like this, the mode, the mean, and the median are all at the same spot. Skewness equals 0. Now, what happens if we start having some skewness to the right, some positive skewness? Then, there are some new outliers here. So what does the mean do? The mean kind of follow it. The green moves over to the right. So far, the median has not moved yet. Well, we spread things a little bit further out, and we take some of the data from here and we put it to the right. Then, yeah, you have more outliers. Then the mean moves further. It moves over here, but in the meantime, the median also moves. And then you make more and more outliers, the mean moves even further along, and the median kind of like slowly moves. So in the beginning, there's zero difference between the mean and the median, and there's zero skewness. And there's some distance between the median and the mean, and there's some skewness. And there's more distance between the median and the mean, and there's more skewness. That's the idea behind the Pearson skewness coefficient. If I take mean minus median, then I should see the skewness. The more the mean gets away from the median, the bigger the skewness, the more outliers there are out there on the right. So this difference reflects the skewness. But we cannot just use that difference as a measure of skewness. So for example, let's take the bottom distribution here. The median is at 5 and the mean looks like 6.2 or something. So 6.2 minus 5 is 1.2. But let's say if I change my units, so for example, these could be in dollars. And these could be in dollars, then the mean minus median is $1.2, which is $1.20. 1.2. Well, what if I change units? It's the same data, but instead of measuring in dollars, I'm measuring in cents. So $5 becomes 500 cents, $10 becomes 1,000 cents, and $15 becomes 1,500 cents, 1,500 cents. Well, now the median is at 500 and the mean is at 620 cents. And I subtract, I get 120. If I only look at the difference and I see that, oh, this was 1.2 and it measures the skewness, and this is 120, it measures the skewness. Oh, it looks like it's 100 times more skewed, right? That's what I would have thought, except that it isn't. It's the same data. It's the same graph. It's the same distribution. All I did was change units. So the scaling, I want my measure of skewness not to be affected by the scaling. If I change units, this number should not change. That's what I want, right? So I need to standardize the measurements, and I standardize it by dividing by the standard deviation. Dividing by standard deviation is a pretty common way of standardizing measures because any change in units or scaling will cancel out from the numerator to the denominator. Those of you who took or are taking statistics will recognize that we did the same thing with the z-score. Z-score is measured by x, which is the data point, minus the mean, divided by standard deviation. X minus the mean measures the distance how far a data point is from the mean. But we don't want that to be affected by the scaling either. So we divide by the standard deviation to standardize it. So that's what we did in z-score, and that's what we're doing here, mean minus median divide by standard deviation, and that should measure your skewness. This should be the formula for skewness, except it's not. It's not the formula I wrote down at the beginning of the video. Let's look at that again. The Pearson skewness coefficient was this. It's got an extra factor of 3. Where's that coming from? So that's a good segue into the second part of this video. I'm going to explain where that number 3 came from. It came from the fact that originally people didn't want to look at mean minus median as a measure of skewness. Now remember what we know about skewness. The more skewed the distribution, the more the mean goes off. But the median also kind of goes along, right? Sometimes it does, sometimes it doesn't. So people didn't really like it as much. They want to just concentrate on one thing that moves, and that's the mean. We know the mean is going to go along with the skewness. So this is what people want to look at. They want to know how far the mean moved off from where it used to be. Well, where was it? It used to be where the mode is. So they want to measure the skewness by how far the mean moved off from the mode. They wanted this. They wanted mean minus mode. And then they also want the scaling, so divided by standard deviation. This is what they wanted originally. And in a lot of ways, it is a better formula than the one with the median. However, in practice, in real life, it turns out to be hard to do because so originally, this is what people wanted. And in a lot of ways, it's a lot better formula than mean minus median. But there's a problem with this. If you have a large data sets in practice, in real life, especially when you don't have complete data, you don't have data on whole population, you only have like a sample of it, even a big sample. It's kind of straightforward and kind of easy to estimate the mean. It's pretty straightforward to estimate the standard deviation, but it's really hard to estimate the mode. Whereas it's also kind of easy to estimate the median. So people said, what if we switch from mean minus mode to mean minus median? And people go, yeah, sure, why not? Especially since we know that there is a relationship between the mode, the median, and the mean. That relationship is not taught as much anymore. Now a lot of people know about it. I didn't know about it until I looked it up. But it used to be taught pretty commonly way back when in the 1920s and 30s. And the relationship is like this. The mode is approximately equal to, not exactly equal, but approximately equal to the mean minus 3 times the difference between it and the median. If you have the mean over here and the median over here, and there's a distance here, then the mode is 1, 2, 3 times. The mode is somewhere near here. Not exactly, but approximately somewhere down there. That's a relationship that used to be well known. Let's check it out with the data sets we saw earlier. The symmetric distribution. Mean minus median is equal to 0. So 3 times that is equal to 0. And so if I take mean minus 3 times that, I got mean minus 0, which is equal to the mean. And in this case, it is equal to the mode because it's symmetric and the mean and the mode are equal. So in the case of 0 skewness, this works out. That works. Let's take a look at distribution 2. This distance is about 0.5. And so 3 times that is about 1.5. The mean is about 3.5. This is 5. This is 4. This is 3. So the mean is about 3.5. 3.5 minus 1.5 is equal to 2. And so we expect the mode to be here. And the actual mode is at 3. And so it's kind of approximate, kind of not, maybe. So this is a little bit iffy, maybe. Distribution 3. Mean minus median is about 0.5. And I multiply that by 3. I got 1.5. The mean is at about 4.5. And I subtract that. I get 3. And the mode is at 3. So that works again. Now I get to the last distribution down here. The mean is about 6.2 maybe. And I take 3 times that, get 3.6. And I take the mean, I subtract 3.6. 6.2 minus 3.6. I get 2.6, which is about here. Whereas the actual mode is at 3. So yeah, it's also kind of close. Yeah, it's mostly true that the mode is mean minus 3 times the difference between mean and median. So let's come back here. We have the formulas for skewness that people used to have, mean minus mode divided by standard deviation. But we also have the approximation mode is about mean minus 3 times mean minus median. So now we want mean minus mode. Well, let's do some algebra. I can take mean minus both sides. Mean minus this is about equal to mean minus all of that. So the right-hand side becomes mean minus, first of all, minus the mean, and then minus the 3 times. The minus distributes, so it becomes a plus, 3 times mean minus median. Well, the mean minus mean cancel, so mean minus mode is equal to 3 times the mean minus median. So I substitute it in here. I have 3 times mean minus median divided by standard deviation. So that's how it worked. We started with mean minus mode, but because of difficulty carrying it out in practice, we replace it by 3 times mean minus median divided by standard deviation, and that is the Pearson coefficient of skewness. All right. That was a lot of fun, actually, for me. I hope you had a lot of fun, too. Like, share, and subscribe for more contents, and thanks for watching. Bye.